running. Processor affinity takes several forms. We have soft affinity, that when an operating system has a policy of attempting to keep a process running on the same processor, but not guaranteeing that it will do so. This is soft affinity. Second, hard affinity. Here, the operating system will attempt to keep a process on a single processor, but it is possible for a process to migrate between processors. In contrast, some systems provide system calls that support hard affinity, allowing a process to specify a subset of processors on which it may run. Many systems provide both soft and hard affinity. The main memory architecture of a system can affect processor affinity, like this figure. This figure illustrates an architecture featuring non-uniform memory access, in which a CPU has faster access to some parts of main memory than to other parts. Typically, this occurs in systems containing combined CPU and memory boards. The CPUs on a board can access the memory on that board faster than they can access memory on other boards in the system. So, look at this CPU. If they access this memory, it's fast. If it accesses this memory, it's slow, because this memory is on the same motherboard with this CPU, but this main memory is on different motherboard. So this is non-uniform memory access. Okay. If the operating system's CPU scheduler and memory placement algorithms work together, then a process that is assigned affinity to a particular CPU can be allocated memory on the board where the CPU resides. So if there is a process executing on this CPU, of course the data section and the text section will if residing in this memory, then the process will execute fast, compile this memory, of course. So the third section, load balancing. On SMP systems, it is important to keep the workload balanced among all processors to fully utilize the benefits of having more than one processor. Otherwise, one or more processors may sit idle while other processors have high workloads. Load balancing attempts to keep the workload evenly distributed across all processors in any SMP system. It is important to note that load balancing is typically necessary only on systems where each processor has its own private queue of eligible processors to execute. On systems with a common run queue, load balancing is often unnecessary, because once a processor becomes idle, it immediately extracts a runnable process from the common run queue. It is also important to know that, however, that in most contemporary operating systems support SMP, each processor does have a private queue of eligible processes. There are two general approaches to load balancing: push migration and pull migration. With PushMigration, a specific task periodically checks the load on each processor, and if it finds an imbalance, evenly distributes the load by moving processes from overloaded to idle or less busy processes. Poor migration occurs when an idle processor pulls a waiting task from a busy processor. Push and pull migration need not be mutually exclusive and are in fact often implemented in parallel on load balancing systems. For example, Linux ULE scheduler for FreeBSD. Section 4. Symmetric multisliding. Symmetric multisliding provides multiple logical processors. It is termed hyper-threading technology on Intel processors. Each logical processor has its own architecture state, which includes general purpose and machine state registers. Each logical processor is responsible for its own interrupt handling.